We're going to talk about these quadric surfaces, specifically the non-degenerate quadric surfaces. So these are the most interesting cases. And there are 5 types of quadric surface that are non-degenerate. There's an ellipsoid, there's hyperboloid of 1 sheet or 2 sheets, and then 2 different paraboloids, an elliptic paraboloid and hyperbolic paraboloid. So for each of these types of surface, we're going to go through a number of steps to familiarize ourselves with them. So first we're going to go over how can we identify the type of surface. That's an important thing. If you're just given an equation, how can you figure out which of the 5 it is? And again, this is not a completely general quadric surface we're looking at. We're assuming that it's in a certain standard form, meaning that its axis is the x-axis, the y-axis, or the z-axis. So there's no mixed terms in any of these. Then we're going to look at the traces parallel to each of the coordinate planes. Find the easiest method to sketch the graph of the surface. So for each one, there's a certain way that you can go about to kind of sketch it the easiest. Usually what that means is you're going to look at one set of traces. So you're going to say, I'm going to take the trace in one of the coordinate planes and then see how those traces change as I move up and down in the direction of the axis. And there's usually one axis that works the easiest. We're going to note any features of the graph particular to the type of surface. So some of them do have some particular features. And then we'll go online and use CalcPlot3D and GeoGebra to manipulate the graph, so really get better graphs of these that you can play around with, interact with some parameters, and also visualize the traces. So on the GeoGebra one, I already showed you this in the previous video, you're able to look at the graph and then look at each of the traces and see them directly on the graph. So we'll go ahead and do that too. There's a lot we could do with this. You could really study these in depth and say a lot about them, but we're just focused on basic properties. All I really am wanting you to be able to do with these primarily is just identify the type of surface, so which of the 5 types, or whether it's a degenerate one, whether it's a cone or one of the cylinders, and just be able to sketch a graph of it and just know the basic features of the graph. That's and the traces, and that's really about it. We're not going to go into any of the properties or anything like that. So one thing, if you want to understand what we're about to do, you really need to think about how familiar you think you are with conic sections. So those are parabolas, ellipses, circles, hyperbolas. If you haven't studied those in a while, or if when you hear those terms, you feel a little bit of panic, you might want to go back and think about them, review your notes from previous classes, or look them up in a book or online, because we're frequently going to be using these. I'll just assume that you know what a parabola looks like, you know how to sketch it, you know what an ellipse looks like and how we could sketch that. So you really go back, and you don't have to go back and get all the technical details. So for instance, if you go back and study ellipses, you don't have to go back and talk about the foci and or if you're doing parabola, don't worry about the directrix and the focus. Just, the basic properties. What does it look like? How can I sketch it? And so on. And the reason is that these curves show up as traces. So when you eliminate one of the variables, which is what you do when you get one of these traces, you're left with a second-degree polynomial in 2 variables, and that's going to be one of these conic sections, or maybe a point or a line or 2 lines. But it's going to be, in general, one of these conic sections, so you need to know what those look like. So we're going to start by looking at ellipsoids. Ellipsoid is probably the easiest of the 5 to think about and sketch. So the best way to think of an ellipsoid is it's like a 3-dimensional version or analog of an ellipse. You just go up one more dimension. So how do we tell that we have an ellipsoid? So first of all, what you want to do is get all the variable factors on one side and the constant on the other, and then notice that on the left-hand side here, here's the important thing. If you look at these 3 terms, Notice that those are all quadratic terms. In other words, there's no linear term. There's no x term, y term, or z term. And also, all the coefficients are positive. All the coefficients are positive. So if you have any of these negative, that's when you get one of the other ones that we're going to talk about later. And also we have the positive term on the right-hand side. If we had a negative term on the right-hand side, this would be nothing because you'd have a sum of squares equaling a negative number, which is not going to happen. All right, so we're going to talk about, over on the side here, I'm going to put the, what we'll call the kind of standard form. So all I mean by standard form is this is just the kind of form that you're looking, you can get it into so that you can graph it the easiest and see what's going on. So the usual standard form given for an ellipsoid that's centered at the origin with the coordinate axes as kind of the axes would be x squared over a squared plus y squared over b squared plus z squared over c squared is equal to 1. And if you think about when you're studying ellipses, this should make a lot of sense because the standard form for an ellipse that you are usually shown to get it into if it was centered at the origin was x squared over a squared plus y squared over b squared equals 1. So all we're doing here is we're just adding an additional z squared term. It's very similar. So let's talk about the traces here. So that's the next thing we're supposed to do here. So the traces, now normally we would have to look at the traces separately, whether x, y, or z are held constant. But in this case, it doesn't really matter because if we hold x equal to a constant, or y a constant, or z a constant, when we go to look at what's left over, since these all have positive coefficients here, we're going to get the same type of curve. And what's going to happen is, if you imagine, let's say x is equal to, I don't know, 3. If x is equal to 3, then you get 9 for that first term. You could subtract it over, and you just end up with 9y squared plus 4z squared is equal to 27, say. So the point is that you're going to get two positive quadratic terms, and then on the other side, you're either going to get a positive number, in which case you're going to get an ellipse, or if you get 0 or negative, well, if it's 0, I guess it would be exactly 1 point. That's kind of the exceptional case, and if it's negative, you just get nothing. So the traces are either nothing or ellipses. So I'm not going to mention if you get no traces, but in this case, they're all ellipses. That's not going to be for most of the cases. For the other ones, usually, like one of the traces in one direction will be ellipses, maybe in another it'll be hyperbolas, and another one it's parabolas. So it's not really the case that all the traces in all three directions are the same, but it is here. Okay, now another thing we can get that's very useful here is to look at the intercepts. So if you go to the standard form here, the x-intercept, if you set y and z equal to 0, you get x squared over a squared equals 1, which means the x-intercepts are going to be plus minus a. So if you get it in that form where you have 1 on the other side, you can just read off from the square roots of the denominator. Again, this is very similar to when you studied ellipses, where you could read off the intercepts just from looking at the denominators. Okay, z-intercept plus minus c. Now, what is the easiest way to graph these, to sketch the graph? So the easiest way to sketch the graph is to look at the traces in each coordinate plane, the xy plane, the yz plane, the xz plane. So the easiest way to graph is to use the traces in each coordinate plane. And we do that by using the intercepts that we got above. So, okay, so let me go ahead and show you kind of what this would look like. Okay, so ours was, just a second here. We were looking at x squared plus 9y squared plus 4z squared is equal to 36. So first thing we want to do is divide through by 36. everything through here by 36. So we get 1 on the right, and we see that it's really x squared over 36 plus y squared over 4 plus z squared over 9 is equal to 1. Okay, so this tells us our x-intercepts, since 36 is 6 squared, our x-intercepts are going to be plus minus 6, go off in this direction. Again, just do the best you can here. 1, 2. Okay, that's pretty close. And then we need to do, in the y direction, we're going to go 2. So 1, 2. And off this direction. And then in the z direction, 3. And then negative 3. Okay, so this is going to be interesting because I'm doing this with the pen. So let's do the traces in each coordinate plane. So if we start with the xy. Okay, so the xy trace is going to be an ellipse that goes 6 units in the x direction and 2 units in the y direction. So that's going to be, I don't know, something like this. Okay, so that's the ellipse in the xy plane. We also get an ellipse then in the xz plane. So in the xz plane, we're going 6 units in the x direction, 3 units in the z direction. So that's going to give us this particular ellipse. And then we've got the one that's in the yz plane, which you go 2 units in the y direction and 3 units in the z direction. All right, so that's as good as I can do, I think, by hand. And really, this is all you need for the sketch. You should be able to kind of see what the surface looks like from this. So let's go ahead and, well, let's go ahead and note there's a feature here. So note that, so one important feature of the ellipsoid is the ellipsoid is the only bounded quadric surface. So what I mean by that is it's the only one that doesn't go off, shooting off to infinity. So you could put it inside of a box, a finite box. So this is the only quadric surface that is bounded. All right, now we're going to go to the graphing stuff and get maybe a little bit better picture of this. And there it is, x squared plus 9y squared plus 4z squared equals 36. You can see it definitely has this kind of shape that we got. And I can zoom in here, and you can see, yeah. So that's an ellipsoid. And here's the GeoGebra graph. So there's our ellipsoid. And let's look at the different traces. So if we set z equal to a constant, we get the ellipses going up and down. So you can see those ellipses. Note at the very top, so right there, or at the very bottom, it just goes down to a single point. And if you're above or below it, obviously there's no trace. The traces parallel to the YZ plane just run this direction. Okay, very similar. And those are those. So these are all ellipses. All the traces are ellipses. And there, let me put all of them on here. There, now you can see, if you put all the traces together, you really get a good picture of what's going on. Let me put these, let me put them on the coordinate planes here. Go on the plane. 0, okay, 0, 0, 0. So this is what it should look like if you do exactly, so that's what I was trying to graph, right? I was trying to graph these traces in the coordinate planes. If I was a perfect artist, that's what it would look like. Next we come to the hyperboloids. So we've got a hyperboloid of one sheet here. So how do we recognize a hyperboloid of one sheet? So if we look at these three terms, so again, notice these are all quadratic terms, and we still have a positive constant on a positive term on the right-hand side. But notice now we've got 2 positive and 1 negative. So exactly 2 positive on the left-hand side. So that's how you know that you're in this case. You get the positive constant on the right, just got quadratics on the left, 2 positive, 1 negative. What's the standard form for these? So the standard form is going to be one of 3. So it depends on where the minus sign is. So standard form is either going to be, x squared over a squared plus y squared over b squared minus c squared over c squared equals 1, or maybe it's the y squared that's negative, or maybe it's the x squared. Okay, so one of these 3. In this case, we've got the last one here. So let's talk about the traces. Now this depends on which of the 3 forms it is, but it's different from the ones that have positive and negative terms. So in this case, if we look at x equals a constant here, what we're going to get is ellipses. Because if x is a constant, then you're going to add it to the other side. You're going to get, positive y squared plus positive z squared is equal to some positive number. So those are going to be ellipses. If either you're looking at the traces y equals a constant or z equals a constant, then you're going to get 2 quadratic terms with opposite signs. So you're going to get hyperbolas. Again, don't think of it in terms of it's just x. It's the one that has the negative term. So just to be clear, this is not always x. It's the term with negative coefficient. And this is the axis that we really want to direct along to sketch the graph. So the easiest way to sketch is to use traces directed along the axis that corresponds to the negative quadratic term. So for us, in this case, it's the x-axis. And a nice feature of this is if these ellipses, the traces that are ellipses, if those are circles, this actually turns out to be a surface of revolution about that axis. So the way you get one of this, you get this surface of revolution is you actually take one of the branches of the hyperbola. You don't take the entire hyperbola. So you just take one piece of the hyperbola, and then if you revolve that around the axis, then that generates this curve, this surface. All right, so let's set x equal to 0. So what we're going to do is look at the traces parallel to the YZ plane. So if x is equal to 0, we're looking at the intersection with the YZ plane, and that's going to be y squared plus 4z squared is equal to 36. Which, after we divide through by 36, that gives us y squared over 36 plus z squared over 9 is equal to 1. So this is an ellipse where we go 6 units in the y direction, and then 3 units in the z direction. Okay, so something like this. Now, let's look at just a couple more. Let's see. Let's take x equals to plus minus root 12. That seems like a strange value, but you'll see why in a second. So if x is plus minus root 12, we get y squared plus 4z squared minus 9 times 12 is equal to 36. 12 times 9 is 108. And after adding 108, we get y squared plus 4z squared is equal to 144, and then we're going to divide through by 144. So y squared over 144 plus c squared over 36 is equal to 1. So now we're going to go 12 in the y direction. So now square root 12 is between 3 and 4, so 2, 3. So somewhere about there. 1, 2, 3. Okay, somewhere around there. we have to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then we're going to go about 6 up. And the same thing here. Now this one's going to go behind here, so I'm actually going to do dashed. I'm going to dash behind there. And then it comes out this way. This one, we've got this piece going up here. Again, dashed here. Comes out here. Okay. So kind of maybe a little bit tricky to see what's going on here. What I'm going to do now is, since we know the other traces are hyperbolas, what ends up happening is this ends up going out like this. And this is not the best graph. And so these ellipses end up just getting bigger and bigger as you go out. Okay, so you start with an ellipse in the center. It's the best way to think of this is like it's a circular tube with an ellipse in the middle instead of a circle. And then as you go out either direction, the tube just gets wider and wider. So the ellipses just keep getting bigger and bigger, and it's an infinite tube. I guess is or infinite cylinder is the best way to think of it. Okay, so this is what I was trying to draw. Now, you can see here, let's move it a little bit this way. So this is what I was saying, it's kind of tricky to hear because we're looking through the middle of the tube, kind of. A better view would be if we looked along one of the other axes, like if I move it this way. Now you can see there, you can see the middle, there's the ellipse in the middle, and then you can see it opening up either direction. Okay. There. Now, yeah, this is the best kind of view here. But I kind of had to shift we had to shift our viewpoint of the axes. And here's what it looks like on GeoGebra. So you can see it's the same kind of shape. Now let's look at the traces. So the traces that we were looking at to graph it were these ellipses. So those ones are the ones that look like where we got x equals to a constant. So those were these. So there's an ellipse. And so this is what I was saying, as you go out, there we go. As we go out either direction, see the ellipses are getting bigger and bigger. So the middle there, smallest ellipse, and then the ellipses get bigger and bigger as you go out. Now for the other ones here, you can see that the other traces are hyperbolas. So there's a trace in the xy plane. You go up. So notice that there's a point here. Notice the hyperbolas start off one way. They're oriented one way, and then they get closer and closer until there's two lines, and then they actually flip and they go the other way. Okay, so that's an interesting thing that happens with the hyperbolas. You can see the same thing down here. Go and then see how it switches. Okay, and then the other ones here. So there's the other hyperbolas. They do the same thing. Okay, so the traces are ellipses in one direction and then hyperbolas in the other two directions. And here's all the traces in the coordinate planes. We get it right at 0. There, right at 0. So we've got the ellipse there and the two hyperbolas in the other directions. All right, so that brings us to the hyperboloid of 2 sheets. So what's the difference between 1 sheet and 2 sheet? How do you tell the difference? So again, we got, look at our 3 terms here. So we got all quadratic terms. Again, we want to get the positive term on the right. But now look at the signs. Whereas before we had exactly 2 positive terms and 1 negative, here we have exactly 2 negative terms and 1 positive. So that's the difference. 2 positive and 1 negative, it's 1 sheet. 2 negative, 1 positive, it's 2 sheets. The standard form. Now, again, there's going to be 3 versions of this, depending upon which is the positive one. So you're either going to get something like, x squared over a squared minus y squared minus z squared, or you could get y squared, or you could have the positive term be z squared. So one of these 3. Now, in this case, we're in the case of the second one here. So we're looking at this one. All right, let's talk about traces. So for our particular equation up here, if you look at the traces where y is a constant, so parallel to the xz plane. So let's say we take y equal to 0. Then we're going to get x squared plus z squared is equal to -4. So that's not going to be anything. So if y is too small, you get nothing. But notice if we solve for, if we let y equals to k, we just get x squared plus z squared is equal to 4y squared minus 4. So if y is too small, the point is that this right-hand side here, this is going to be negative. So y has to be a certain amount of certain magnitude. But once you get past that point, this is positive on the right-hand side, you're going to get an ellipse. So eventually we get ellipses, I'll say, if y is large enough in magnitude. Now with x equals to a constant or z equals to a constant, what's going to happen is, so you could shift that term to the other side, and the remaining two terms will always have opposite signs, which means you're always going to get some hyperbolas, so those are always hyperbolas. The easiest way to graph this, again, is to direct it along one of these axes, and you want to, with these hyperboloids, you want to think about directing it along the axis that's the oddball. So before, right, we had two positive terms and a negative one, and we ended up directing it along the axis corresponding to the negative coefficient. So here we're going to direct the traces along the axis corresponding to the positive coefficient. So it's just always the one that's the oddball that doesn't match the other ones. Okay, so we sketch using traces directed along the axis corresponding to the positive coefficient. Let me just to emphasize here, this is always the one with corresponds to the term with positive coefficients. So one interesting feature to notice about this type of surface is this is the only non-degenerate quadric surface that's made up of two disconnected pieces. So all the other surfaces, we would say that they're connected in the sense that they're all one piece, right? You can get from any point on the surface to any other point on the surface. You can go through there. Here, there's two disconnected pieces, so if you're on one piece, you can't get to the other one without jumping through, empty space. So only quadric surface, disconnected pieces. All right, so we had 4y squared minus x squared minus z squared is equal to 4. So let's take, say, well, first of all, let's divide through by 4. So the standard form for us would be, we take y equals 0. We don't get anything, so there's nothing at the origin here. And how big does y have to be before we start getting something? Well, let's see, we would need x squared plus z squared to equal 0, and that'll happen when y squared is equal to 1, which is going to be at y plus or minus 1. So this is going to start opening up, both pieces are going to start opening up at y equals 1 and minus 1. Should go this way. And so it's just going to be a single point there. Now what if we increase y to a certain value? What if we increase y to 2, plus minus 2? Y is equal to plus minus 2. Then we're going to get 4 minus x squared over 4 minus z squared over 4 is equal to 1. And this is going to be, let's see if we subtract 4. So it's going to be x squared over 4 plus z squared over 4 is equal to 3. Okay, and then we divide through by 3. We'll get 12 in the denominators. So square root of 12 is between about 3 and 4. So what we end up getting is a circle Well, actually, it's a circle of radius square root 12. Okay, so we go out here and here. So here, we need to go up 3, about 3.5, let's say, bigger and bigger. So let me draw a couple more of these. So you are beginning to see why in multivariable calculus classes, I don't really require anyone to do any graphing on an exam. I've never done that because I don't do it very well myself. So, you know, just try and do the best you can on these. You know, at least going through the process, you get a feel for what's going on, and then you can always use the websites or the software to graph them. But I was never able to do this graphing in 3 dimensions. I have enough trouble with 2 dimensions, drawing stuff. 3 dimensions, I just can't handle it. So I will never expect students to graph something from hand like this on an exam. So something like this. Well, it sort of looks like, if I move it this way, you can sort of, that's kind of like what I was trying to draw. You can see it's got the 2 pieces there opening up. If I zoom out, okay, so now you can see, well, okay, so now you can see. You can see there's just that little piece there between 1 and -1 where it's not, there is no part of the graph there. All right, and here we have the same graph here, and let's put in these elliptical traces. So that would be, oops. Yeah, so notice when I'm between 1 and -1, so I'm between 1 and -1, I don't see anything there. Finally, when I get less than -1, you start to see those ellipses getting bigger and bigger. And then when I get over to y equals 1, then I get the ellipses getting bigger and bigger that direction. And you can see the hyperbolas going up and down, like this. All right. And then the other hyperbolas in the other direction, going this way. Okay, so if we put all 3 of these on here, now you can really get a feel for what's going on. Put these. Okay, so there you can see there's the 2 hyperbolas in the 2 main coordinate planes. Whoops, let me do, okay, there's the 2 hyperbolas, and then I'll do one of these ellipses out here, up there. Okay, so hopefully that gives you a good idea what this type of surface looks like. Next we look at the paraboloids. So it's two types of paraboloids, elliptic paraboloid and hyperbolic paraboloid. The nice thing about the paraboloids is these are very nice to think about just as a function. So think of it as a graph of a function. So you can see here x equals y squared plus 4z squared. That's just a function of y and z. X is a function of y and z. So it could be z, it's usually going to be z as a function of x and y. It could also be y as a function of x and z. So how do we identify these? Well, here's how. There's always a linear term. So these are the only ones, these last 2, these are the only ones that have a linear term. It could be x, y, or z depending on the axis. But so that's the first thing. You look at the linear term. Now you have to determine whether it's elliptic or hyperbolic. And you do that by looking at the other 2 terms, put them on the other side. And if these have the same sign for their coefficient, so both positive or both negative, then it's going to be an elliptic paraboloid. So the same sign on the quadratic terms. All it's going to mean is if they're both positive, it's just going to be opening up or to the right, you know, in the positive direction. If they're both negative, it just opens in the opposite direction, down or left. The standard form usually given for these. So it's either like x squared over a squared plus y squared over b squared is equal to z over c. Or the other combinations, right? X squared over a squared plus z squared over, I guess say b squared. I don't know how. Yeah, I guess how you label these doesn't really matter. y over c, or y squared over... There may be some way that I'm supposed to be labeling these a little bit differently, but I'm not really worried about that. It's just that you can recognize which one is a linear term. Now c here in each of these could be positive or negative. So if it looks like these are all positive coefficients, if c is negative, you multiply through by a negative. That's where you get both negative. But the important thing is just you're able to recognize that it's one of these forms. All right, let's talk about the traces. So first, the traces we're really interested in are the ones that are directed along the axis of the linear term. So if we look at, say, x equals a constant here, we see that we're always going to get ellipses. But the sign of k has to match the quadratic term sign, right? So if I put in a positive value for x here, then I'm going to get an ellipse. If I put in a negative value, it's just going to be nothing. So k and the quadratic terms have to have the same sign. What about the other two types of trace? So if y is equal to a constant, or z is equal to a constant in this case. So what you should see here is if one of those terms on the right is a constant, then we just get x is a quadratic function of y or quadratic function of z. That's just a parabola, right? It's just like, you know, y equals x squared or x equals y squared. So here we get parabolas. And again, it's not always x. This is the corresponds to... It's always the variable that corresponds to the linear term. And the easiest way to graph this is to use the traces directed along the axis that corresponds to the linear term, because we want to think of it as a function of y and z here. And again, a feature of this is that this is, we can regard it as a graph of a function. Not the graph of two functions, you know, so we don't have to consider plus and minus. This is entirely the graph of a function. So it's either, you know, x equals a function of y and z, or y equals a function of x and z, or z is equal to a function of x and y. So one of those three. And you can kind of think of this as it's kind of a three-dimensional version of parabola, because what it's saying is it's a function of two variables, but each of those variables are allowed to go up to quadratic. So it's kind of the best generalization of a parabola in 2 dimensions. All right, so let's see if we can sketch this one. This one is, it's not as easy as the ellipsoid. The ellipsoid is kind of the easiest one, but this one may be the second easiest. The last few have been kind of difficult. So let's look here. So we had x equals y squared plus 4z squared. All right, so let's just look at this as x as a function of y and z. So the best way to think about this is to think about which direction it's opening. So since these are both positive coefficients, not negative, we know in the x, so as a function of y and z, this is going to open in the positive x direction. So it's going to open in this direction towards us. It does go through the origin. Let's set, say, if we set z is equal to 0, we get x is equal to y squared. Okay, so that's telling us that in the xy plane, we just get an ordinary parabola. We also get a parabola. We get x equals 4z squared. So in this case, as z goes up or down, it opens this way. So this is something like that. And then as you go out, you get these ellipses. Again, I think this is the best I'm capable of. This is pretty good. Hopefully you get an idea. Let's look at the graphs on the software. All right, there it is. You can see it opening up kind of like that. I could even get some more detail on here. Idea. Whoops. Stop. I back up. All right, so you get the idea here. It's kind of like the three-dimensional version of a parabola opening up. And there it is. And if we look at, so the parabolas I was trying to get. So at first we set, what was it? Z equal to 0. It'd be these. There we go. So I was looking at these parabolas. And then the other types of parabolas are the ones where you set y equal to 0. And so that's these going. So you can see they're slightly different direction. And then in the x direction, we got these ellipses. Okay, so ellipses and parabolas are the traces. Last but not least, hyperbolic paraboloids, the other type of paraboloid. So the only difference between this and the elliptic paraboloid, when you're looking at it, notice we've got, again, a linear term here. And then on the right-hand side, it doesn't really matter whether the linear term is positive. So you don't need to look at the sign of the linear term. What you want to look at is look at the quadratic terms have opposite signs. If you have a linear term on one side, quadratic terms with opposite sign on the other side, then you've got a hyperbolic paraboloid. So the standard forms here. So these would be either x squared over a squared minus y squared over b squared is equal to z over c. Here c could be positive or negative. So if c is negative, then you would switch the sign. Then it would be y squared minus x squared. Or you could have quadratics being x and z, or you could have the quadratics being y and z. Again, I'm not sure exactly if the a, b, and c are being labeled exactly how they should here. It's not really the most important. Just notice in each case that we've got a linear term, two quadratics of opposite signs. In this case, obviously we're in this first case here. Now the trace, let's look at the traces. So if we set y equals to a constant, notice that we're going to get z equals x squared plus some number. So that's going to give us parabolas. Notice if we set x equals to a constant, we're also going to get parabolas, but they're going to be opening in the opposite direction. So it's actually an important thing to note here. So these two parabolas open opposite directions. This function, so if you think of this as a function, this is the simplest kind of function to analyze what we're going to call later saddle points. So, and you'll see this in the graph, it looks like a saddle. Now if we take the traces where z is a constant, we get hyperbolas. Okay, so parabolas and hyperbolas. With the elliptic paraboloid, we had parabolas and ellipses. So here it's hyperbolic paraboloid, parabolas and hyperbolas. The easiest way to graph this. What's the easiest way to graph this? These are not that easy to graph either. I guess the easiest way to sketch the graph is to start with two parabolas that are in the coordinate planes. So here it would be y equals k. It would be y equals 0 and x equals 0. And what you're going to see here is that these parabolas are going to meet at the origin, but that origin is going to be a maximum for one of the parabolas and a minimum for the other one. And probably the easiest thing to do then is to look at the parabola which opens down and then kind of translate it along the parabola that's opening up. It's kind of hard to say exactly here, but I'll do it in just a second here. Now, a feature here that we'll talk about later, this is the simplest example of a function that exhibits what's called a saddle point. And we'll go over exactly what the definition of a saddle point is, but for now, you just need to know that a saddle point is just something, when we look at the graph, it's going to look like a saddle. That's why it's called a saddle point. All right, here goes. So if x is equal to 0, then we get z is equal to minus y squared. So think about what that's going to look like. It's just an ordinary parabola opening up in the negative direction. So if you look at z and y, so normally this would be like the xy plane for us. So it's just a parabola opening down. And in the other direction, so now if we set y equal to 0, now we get z equals x squared. So now what we're doing is we're going in this direction here, think about going along the x-axis, and it's going to open up. Okay, now what we have to think of now is taking this one that opens down and think about that going along the parabola that's opening up. So what I mean by that is we're going to start with, there's going to be parabola down there, maybe a parabola going down there, and the same way over here. This is really hard to sketch. I guess we could try and note the hyperbolas here. Maybe that would make it a little bit easier. So we got these hyperbolas going this way until we get all the way down to here. They open up like this, and then they open up the other direction. Again, let's just go to the software. Alright, so we need to rotate a little bit so you can see behind what's going on here. Or I could do this, I guess you can see a little bit more if I toggle transparency. So now you can see, so see how it's got the parabolas that are the ones that are opening up in one direction, but opening down in the other direction. And notice it looks like you could sit on the origin, just like you're on a, like you're a cowboy riding in the saddle. So that's why it's called a saddle point at the origin here. And here it is here. So let's look at the two sets of parabolas. So we got the parabolas going in the y direction. So these are the parabolas that we're opening up, so you can see them. So notice the parabolas that open up, there's actually one of them that reaches, its vertex reaches a maximum. So that's the highest the parabola goes. They're opening up, but then all the other ones are further down from that. So in this direction, what we have is a local minimum. So if I take a slice this direction, notice I get a parabola opening up, I get a local minimum. But if I take the other parabolas, which are going along, going along the x-axis, notice these are parabolas opening down, right? But there's one of them that is the lowest, and at that point, at the origin, if we take this slice, we would say that it has a maximum. So if we take a look at these two, notice we've got, these two. You got two parabolas meeting there at the origin. So if you're looking at the function from one direction, it looks like it has a minimum value, but if you look at it in the other perpendicular direction, it looks like it has a maximum value. That's what we mean by saddle point. That's the nature of a saddle point, is that it has a maximum one way and a minimum the other. Now if you look at along the z-axis, these are the hyperbolas. Okay, so we've got hyperbolas going up and down there. So it's kind of hard to visualize, but that's kind of what it looks like. All right, so finally, that's all of these quadric surfaces. So I hope this helps you to visualize these. We'll be using many of them throughout the semester, so you'll get more acquainted with them. But this finishes chapter 12. The next chapter 13, we're going on to vector-valued functions, and space curves.